Example 3, find the area of the region common to the two regions bounded by the following curves. We have r is equal to negative 6 times cosine theta, which will give us a circle, and r is equal to 2 minus 2 times cosine theta, which will give us a cardioid. And this is, in fact, what we will have. And we want to find the area of the region that is inside the circle and also inside the cardioid. And you can see the region in the lesson that I carefully shaded, but you can try to visualize that here as well. So it has to be the overlapping of the region inside the green cardioid and the red circle. And that region is symmetric about the line containing the polar axis, or if we were in the Cartesian plane, that would be the x-axis. So you can find the area of the region above that line and multiply by 2. So let's see how we can see that, how we can see what the limits of integration should be and what integrals we will write. So if we start at theta is equal to 0, and then I move the slider going from 0 onwards, you can see that the circle is being sketched starting at this point here, which would be when theta is equal to 0, cosine of 0 is 1, and you get r is equal to negative 6. So although theta is 0, because r is equal to negative 6, I don't get a point here. Instead, I get a point over here on the opposite ray from theta is equal to 0. And then on the other graph for the cardioid, when theta is equal to 0, cosine of 0 is 1, 2 times 1 is 2, 2 minus 2 is 0. So I get a point at the pole for the cardioid when theta is equal to 0. And then I start sketching each curve as theta increases from 0 all the way to pi over 2. And when theta is equal to pi over 2, the circle is now at the pole, and the cardioid has a point here with coordinates r theta, where r is equal to 2 and theta is equal to pi over 2. And as theta continues to increase from pi over 2, the two graphs have a point of intersection at a common value of theta, 2 pi over 3. And as I continue to increase theta, going to theta is equal to pi, you can see that the cardioid has a point here at 4 pi, r theta, 4 pi, because when theta is pi, cosine of pi is negative 1, 2 times negative 1 is negative 2, and 2 minus negative 2 is 4. So we have the point r theta, 4 pi on the cardioid when theta is equal to pi. And on the circle, when theta is equal to pi, cosine of pi is negative 1, and negative 6 times negative 1 is positive 6. So you have this point on the circle 6 units away from the pole on the terminal side of the angle pi radians. And then as you keep going, you have a point of intersection between the circle and the cardioid at theta is equal to 4 pi over 3. And here we have theta is equal to 3 pi over 2. The circle just gets traced once again. So the circle will be traced twice on the interval from 0 to 2 pi. It is traced once on the interval from 0 to pi. And then the cardioid is traced once on the interval from 0 to 2 pi. The fact that the circle is traced twice on the interval from 0 to 2 pi makes no difference for the problem that we're considering, which is to find the area of the region that is both inside the circle and the cardioid. So, as we've already noted, this particular point occurs when theta is equal to 2 pi over 3. The circle starts being traced from the pole to this particular point from theta is equal to pi over 2 to theta is equal to 2 pi over 3. So those are going to be the limits of integration when you find the area of this subregion here between the purple line and the red circle. So when you find the area of that subregion, you're going to integrate from pi over 2 to 2 pi over 3, and the integrand would be -6 cosine of theta squared. And of course, you have to multiply that by 1/2 because the definite integral is 1/2 times the definite integral from alpha to beta of f of theta squared d beta. And that would give you the area of this region. Now, you have to use the fact that we have symmetry. There's going to be a region that is symmetric to this below the x-axis, or the line containing the polar axis. And if you can see the radial line, theta is equal to 4 pi over 3. That radial line, along with the circle, will define the region that it has the same area as what we just discussed. And then, of course, the other subregion is the region here that I'm showing you. This is the subregion that you now want to write a definite integral to find its area for. And this subregion between the purple line and the line containing the polar axis and the graph of r is equal to 2 minus 2 times cosine theta. It is bounded by the radial line theta is equal to 2 pi over 3, and the radial line theta is equal to pi, and the graph of the polar equation, r is equal to 2 minus 2 times cosine theta. So you're going to write 1/2 times the definite integral from 2 pi over 3 to pi, and the integrand is going to be the equation for the cardioid, which is 2 minus 2 times cosine theta, and you have to square it. And of course, once you have that, you're going to add that to the integral that we had talked about earlier, and that would give you the sum of the areas of these two subregions. But that's only half the area of interest, so you would have to take that sum and multiply by 2, so you get the area of the entire region of interest, which is above the horizontal line containing the polar axis and below the horizontal line containing the polar axis.